Imagine a place in the universe where the very fabric of space and time curls up into an infinitely dense point, so dense that nothing, not even light, can escape its grasp. A cosmic enigma so profound, it defies the laws of physics as we know them. This is the black hole, a phenomenon both terrifying and mesmerizing, a riddle at the heart of modern science. Yet, after decades of study, these celestial mysteries remain shrouded in uncertainty, teasing us with glimpses but withholding their deepest secrets. Black holes challenge us to rethink everything we understand about reality itself. How can something exist where gravity is so overwhelming that it warps not just space, but time? How do matter and energy behave when compressed beyond imagination? The boundary surrounding this abyss, the event horizon, marks a point of no return, a cosmic veil beyond which conventional notions of cause and effect begin to dissolve. It is here that physicists' equations wrestle with contradictions, where quantum mechanics and general relativity seem to speak different languages, and where profound questions about information and existence hang in the balance. Consider this: the event horizon is invisible, yet it defines a realm from which no signals can escape to the outside world. What happens inside remains a matter of speculation, and ideas range from the classical to the bizarre. Some propose that inside lies a singularity, a point of infinite density and zero volume where known physics collapse. Others speculate on exotic alternatives such as fuzzy firewalls or holographic projections that force us to question the very nature of information, memory, and even the fabric of the cosmos. The implications stretch far beyond astrophysics. If black holes can erase information, what does that mean for the fundamental laws of quantum theory, which insist that information cannot be destroyed? Does the universe hide deeper layers of reality intertwined with these cosmic voids? Are black holes, in some way, gateways to other dimensions or parallel universes? And what about their role in cosmic evolution? Do they shape galaxies, or do galaxies shape black holes? The relationship is intricately intertwined, yet the causal links remain elusive. Each discovery about black holes opens new doors and new questions. Recently, the Event Horizon Telescope captured the first ever image of a black hole's shadow, offering a glimpse into this invisible world and confirming many predictions but also highlighting discrepancies that hint at the limitations of our current theories. Meanwhile, advances in gravitational wave astronomy have revealed the violent collisions of black holes across the cosmos, shaking spacetime itself and adding new chapters to their mysterious story. As we embark on this exploration into the unknown, we confront the edges of human knowledge and the universe's most profound secrets. These cosmic beasts may be the key to unlocking a new understanding of reality, one that reshapes how we see our place in the universe, the origin of space and time, and the ultimate fate of all things. Because within the dark heart of a black hole lies not just destruction, but the tantalizing promise of revelation, inviting us to look deeper and to wonder what lies beyond the horizon, waiting to be discovered. To grasp the enigma of black holes, we must first navigate through the fabric of space and time itself, the very stage upon which the cosmos unfolds. Imagine space not as an empty void, but as a vast, flexible canvas, one that can be warped, twisted, stretched, and even torn by the presence of mass and energy. This revolutionary view emerged with Einstein's theory of general relativity over a century ago, a paradigm shift that transformed gravity from a familiar force pulling objects toward one another into a geometric distortion of spacetime. Massive bodies like stars deform this fabric, causing smaller objects to follow curved paths, what we perceive as gravitational attraction. Black holes, then, are regions where this curvature becomes so extreme that not even light can escape the irrepressible pull. But what gives birth to a black hole? The answer lies in the cosmic cycle of stars. When a massive star, many times heavier than our Sun, exhausts its nuclear fuel, it loses the energetic battle against gravity. The core collapses inward in a cataclysmic implosion, compressing mass into an unimaginably dense point. This point, known as the singularity, marks the heart of a black hole. Here, our familiar understanding of physics breaks down. Density and gravity soar toward infinity, defying the known laws that govern matter and energy. Surrounding this core is the event horizon, a boundary of no return, a horizon in space, beyond which events can no longer influence an outside observer. This dichotomy between the singularity and the event horizon is where much of the mystery lies. The event horizon acts as a cosmic veil, concealing the singularity and everything swallowed by the black hole from the universe beyond. It represents a radical frontier where space and time themselves are dragged inward. For an outside observer, anything crossing this threshold appears to freeze, fading, and redshifting into oblivion. Yet, for an intrepid traveler falling in, time stretches out strangely, culminating in a plunge toward a gravitational abyss beyond comprehension. Even in this simple picture, black holes challenge intuition. They force a reconsideration of space, time, and the nature of reality itself. For example, a black hole's gravitational influence is often described as warping space, but it also warps time. The flow of time slows down near the event horizon relative to an observer far away, a phenomenon known as gravitational time dilation. It's as if clocks near a black hole tick ever more slowly, tipping our perception of causality and sequence upside down. What amplifies the puzzle is the variety of black holes thought to exist. Stellar black holes, born from dying stars, are merely one class. Far grander are the supermassive black holes, millions or even billions of times the mass of our Sun, anchoring the centers of galaxies. Their formation remains poorly understood. They might grow through the merging of smaller black holes or by voraciously consuming gas and stars. The scale alone challenges the limits of observation and theory alike. Between these extremes lie the elusive intermediate mass black holes, scarcely confirmed, hinting at a spectrum of gravitational monsters awaiting discovery. An intriguing aspect of black holes is that they are defined by surprisingly few attributes: mass, spin, and electric charge. This property, captured in the dictum that black holes have no hair, means that they erase all other characteristics of the matter they consume. This metaphorical baldness sits uneasily with the principle of information conservation in physics, deepening the conceptual turmoil. Another layer of complexity emerges when considering how black holes interact with their environments. Despite their reputation as cosmic vacuum cleaners, black holes do not indiscriminately devour everything. Matter often forms disks swirling around them, a fierce maelstrom of ionized gas heated to blazing temperatures, emitting torrents of electromagnetic radiation. These accretion disks are among the brightest objects in the universe, shining in X-rays and radio waves, paradoxically announcing the presence of an otherwise invisible black hole. Jets of energetic particles can also blast outward along the rotational axes of spinning black holes, propelled by magnetic fields twisted by relativistic effects. These jets can extend across millions of light-years, shaping their galactic neighborhoods in profound ways. Thus, black holes appear not only as consumers but also as cosmic architects, influencing the formation and evolution of stars and galaxies. Decades of mathematical exploration have revealed that black holes are solutions to Einstein's field equations, but these solutions harbor singularities where the known laws cease to apply. Inside the event horizon, all known physics collapses into uncertainty. While general relativity predicts this singularity, it also breaks down mathematically, signaling the need for a deeper, more fundamental theory uniting gravity and quantum mechanics. This theoretical gap has spurred countless speculations, from exotic proposals like wormholes, hypothetical tunnels through spacetime, to more conservative ideas suggesting quantum effects might smooth out singularities, replacing the infinite density with something yet unknown. The notion that time and space might lose their classical meanings near or inside a black hole unsettles our most basic assumptions. What does it mean for a concept as fundamental as causality to twist or pause? Does the fabric of reality fray or transform? The singularity, perhaps paradoxically, represents not only an end but also a boundary to knowledge where questions outpace answers, and theory yields to mystery. In this theater of extremes, black holes thus stand as more than astrophysical oddities. They are profound cosmic puzzles at the intersection of gravity, quantum mechanics, and information theory. Their study pushes the frontiers of human understanding, demanding innovative mathematics, bold observational strategies, and new philosophical perspectives about the nature of existence. As our instruments grow ever more sensitive, and as new windows into the universe open through gravitational waves, X-ray astronomy, and radio imaging, we inch closer to peeling back the layers cloaking these black holes. Yet, with each advance, the universe seems to remind us that black holes are not merely endpoints but gateways to deeper, more intricate truths about the cosmos. In the silence beyond the event horizon lies a realm where physics blurs, where our scientific maps dissolve into unknown territory. It is the ultimate destination of matter and light, a crucible where time may bend or cease, where the fabric of space is threaded into forms we have barely begun to imagine. Black holes invite us to confront the profound and the mysterious, to question the boundaries of reality itself. Their enigmatic presence challenges us to embrace uncertainty, to push beyond familiar horizons, and to seek the hidden symmetries and secrets woven into the cosmos's darkest depths. At the heart of modern black hole research lies an extraordinary concept known as the singularity, a point where the fabric of space and time itself seems to collapse. According to the prevailing theory built on Einstein's general relativity, this singularity represents a region of infinite density, a place where all known laws of physics break down entirely. Imagine a destiny so extreme that not even light, the fastest thing in the universe, can escape its clutches. This is the core of the black hole's mystery, an existence condensed into a single point, infinitely small yet unimaginably powerful. This theoretical focal point is surrounded by the event horizon, a boundary marking the threshold beyond which escape becomes impossible. But the deeper intrigue spirals inward toward what lies within this veil. What happens when space curves so violently that it funnels all matter and energy into the singularity? Our current understanding suggests that gravity becomes overwhelmingly intense, warping time itself, slowing down clocks to a crawl near the horizon, until time effectively stops inside. In this surreal domain, the conventional distinction between past, present, and future begins to unravel, giving rise to a realm unlike anything we observe in the everyday cosmos. One striking element of the primary theory is the idea that black holes are not merely cosmic traps, but fundamental tests of the limits of physics. General relativity, while remarkably successful at describing gravity on large scales, fails to incorporate the principles of quantum mechanics governing the microscopic world. The singularity represents a crossroads where these two pillars clash. Understanding what really happens at this juncture requires a new, unified framework, a theory of quantum gravity that remains elusive despite decades of effort. Among the leading candidates to resolve these contradictions is the hypothesis of a quantum-corrected black hole interior. Some theorists propose that the singularity is not truly infinite but blurred and softened by quantum effects. Under this view, the black hole's core may be a quantum bounce or a highly exotic state of matter, avoiding the catastrophic infinities that classical physics predicts. If true, such corrections might allow for information to somehow survive or transform, challenging the long-held notion that everything swallowed by a black hole vanishes forever. This possibility introduces profound implications for one of physics' most puzzling dilemmas, the information paradox. First articulated by Stephen Hawking in the 1970s, this paradox arises because quantum theory demands that information cannot be destroyed, yet black holes seem to erase all traces of what they consume. Efforts to reconcile this have led to a variety of bold ideas, such as the holographic principle. This principle envisions that all the information within a black hole might be encoded on its two-dimensional event horizon, much like a hologram storing three-dimensional data on a flat surface. If this is true, then black holes could be understood as cosmic information vaults rather than mere cosmic oblivions. Pushing further into this conceptual terrain, some scientists explore the idea of firewalls at the event horizon, hypothetical energetic barriers that might incinerate any infalling matter, replacing the smooth passage predicted by general relativity with a violent, quantum disruption. This controversial proposal shakes the foundations of the theory, forcing a re-examination of what it means for an observer to cross into the black hole's shadows. Yet, such radical ideas highlight how black holes act as crucibles where our deepest assumptions about spacetime, causality, and quantum theory are stress-tested to their limits. Observational fronts add another layer to this theoretical landscape. The detection of gravitational waves, ripples in spacetime generated by colliding black holes, has opened an unprecedented window. These waves carry subtle signatures about the mass, spin, and even the potential internal structure of black holes. The precise patterns of these cosmic vibrations allow researchers to test competing theories under extreme conditions that no laboratory on Earth can replicate. Meanwhile, the historic imaging of a black hole's shadow by the Event Horizon Telescope project provided the first direct glimpse of the event horizon's silhouette against glowing accretion disks. Together, these experimental breakthroughs shepherd us from abstract equations toward tangible reality. Yet, the main theory also hints at an even stranger proposition hidden in black holes' cores, a concept that challenges the very notion of existence. Some speculative models suggest that the singularity could act as a gateway to other universes or dimensions, a cosmic wormhole where the fabric of reality folds upon itself. While such ideas remain unproven and highly speculative, they underscore how the boundaries of astrophysics blur into the realms of metaphysics and philosophy. Black holes, in this light, are not simply objects to be measured but portals stimulating questions about parallel realities and the nature of the multiverse. The impact of these ideas extends beyond physics, shaping how we comprehend our place within the cosmos. If black holes indeed connect to other realms or store the universe's information in novel ways, then they might hold the keys to understanding the origin of space, time, and matter themselves. The interplay between gravity and quantum theory encoded in black holes could unlock insights about the Big Bang, the emergence of complexity, and the ultimate fate of all things. In grappling with the main theory of black holes, one comes to appreciate that they defy reduction to simple explanations. They emerge as dynamic entities where geometry, energy, and quantum uncertainty converge. Their mechanics invite relentless inquiry into what reality truly means, challenging every classical intuition about the cosmos. Black holes compel us to expand our conceptual horizons, to imagine a universe more intricate and interconnected than ever envisioned. As research continues to unfold, the main theory will undoubtedly evolve, enriched by new discoveries and insights. Each unanswered question beckons scientists deeper into a domain where mathematics and physics merge with awe and curiosity. Black holes stand as towering enigmas, simultaneously terrifying and sublime, drawing us into a profound cosmic mystery that defines the cutting edge of human knowledge. In embracing their riddles, we embark on a voyage toward the heart of existence itself, where the known and unknown intertwine in an endless dance across the universe. As our instruments grow ever more precise, the shadows cast by black holes shift subtly, revealing tantalizing new clues that both illuminate and deepen the mystery. When the Event Horizon Telescope first captured the silhouette of the supermassive black hole in the galaxy M87, it offered a historic glimpse into the warping of spacetime itself. But beyond the iconic image lies a rich tapestry of data about the swirling plasma and powerful magnetic fields that girdle the event horizon, the very boundary beyond which not even light can escape. This maelstrom challenges established models, forcing physicists to reconcile how matter behaves under gravity so intense it dwarfs anything we can recreate on Earth. One of the profound implications emerging from these observations is the apparent role black holes might play in the life cycle of galaxies. Rather than mere cosmic vacuum cleaners indiscriminately devouring everything in their path, they appear to regulate star formation and even the distribution of matter across vast cosmic neighborhoods. The jets that erupt from the poles of spinning black holes, charged with particles accelerated to near light speed, blast energy far beyond the event horizon, seeding intergalactic space and influencing the grand architecture of the cosmos. This interplay suggests black holes are not isolated anomalies but integral agents shaping cosmic evolution on scales both large and small. Meanwhile, theorists wrestle with the inner sanctum where classical physics crumbles. As matter is crushed toward an infinitely dense singularity, conventional equations reach their limits, demanding a unifying theory that seamlessly combines Einstein's general relativity with quantum mechanics. Some proposals, like string theory and loop quantum gravity, envision granular structures to spacetime itself, potentially avoiding the paradox of infinite density. Could these ideas hint at an ultramicroscopic fabric where the singularity's mysteries are resolved? Although definitive proof remains elusive, such frameworks inspire novel ways to imagine black holes, prompting re-examination of what it means for something to exist where time and space dissolve. The enigmatic behavior of information near black holes further muddies the scientific waters. Conventional wisdom held that any information falling past the event horizon would be lost forever, a concept at odds with quantum theory's premise that information cannot be destroyed. This conundrum, known as the black hole information paradox, provoked decades of debate and led to dramatic hypotheses including the idea that information might be encoded on the event horizon itself or somehow emitted back through Hawking radiation. Recent breakthroughs propose that black holes might preserve a subtle holographic record of everything they consume, suggesting the universe at large may be governed by intricate codes tying together gravity and quantum fields. If true, this would reshape our notions of memory and reality on a cosmic scale. Beyond these theories lies the provocative concept that black holes might act as natural laboratories for exotic physics never directly testable on Earth. For instance, some scientists speculate about the existence of primordial black holes formed in the early universe, which could contribute to the mysterious dark matter that holds galaxies together. Detecting such objects would pave the way toward understanding the unseen majority of matter in the cosmos, while also offering insights into the universe's infancy. Additionally, scrutiny of gravitational waves ripples in spacetime produced by colliding black holes has opened a novel observational window into extreme gravity regimes. Each detected wave carries encoded information about the mass, spin, and environment of merging black holes, challenging theorists to refine their models and inspiring new questions about the nature of space and time itself. In a broader sense, the pursuit of understanding black holes underscores a humbling truth: these cosmic behemoths are as much mirrors reflecting the limits of human knowledge as they are objects of study. They reveal the edges where our current scientific frameworks falter, pointing toward the necessity of revolutionary changes in physics. As enigmatic as they are, black holes might well represent the greatest teachers in our quest to decipher the universe's fundamental workings, beckoning us beyond familiar territory into realms where imagination and rigor must work hand in hand. Thus, the scientific expansion surrounding black holes is not just about filling gaps in understanding, but about uncovering the hidden layers of reality that challenge our deepest assumptions. Every observation, every advance in theory, serves as a stepping stone into a domain where space and time intertwine unpredictably, where quantum fuzziness collides with gravitational enormity, and where the profound mysteries of existence continue to elude conclusive explanation. In this light, black holes stand as both frontier and beacon, reminding us that in our drive to explore the cosmos, we are also exploring the boundaries of thought itself, venturing into an unknown vastness whose final revelations remain as thrillingly distant as the stars themselves. Beyond the intricate equations and distance signals, black holes invite us into a deeper meditation on the nature of consciousness and our place within the cosmos. When we confront these gravitational enigmas, regions where the familiar laws of physics collapse into paradox, we begin to question what is truly real and what lies beyond perception. If the event horizon marks a boundary beyond which no information escapes, then what does that say about knowledge itself? Is reality confined to what can be observed, or does it extend into silent, inscrutable realms forever beyond reach? The black hole challenges our conventional notions of existence, compelling us to reflect on the interplay between observation, awareness, and the fabric of the universe. In considering the singularity, a point of infinite density and curvature, we are faced with a convergence of extremes that defy our comprehension. It is a place where not only matter but meaning itself seems to dissolve. This incites a profound philosophical tension. The universe appears capable of creating conditions that shatter our frameworks for understanding, physical, mathematical, even conceptual. From this perspective, black holes are not merely cosmic objects, they are profound symbols representing the limits of human cognition and the paradoxical coexistence of order and chaos. They compel us to ask, if the very foundation of space and time breaks down here, might there be aspects of reality completely inaccessible to thought and language? Moreover, these cosmic enigmas echo ancient philosophical questions about the nature of the self and consciousness. The question arises whether the concept of an inside and outside has meaning when the usual definitions of space and time dissolve. If information can become trapped irretrievably beyond an event horizon, does this suggest a form of cosmic amnesia, a hidden domain where histories are lost or rewritten? Such mysteries resonate hauntingly with the human experience of the unknown, the unconscious, and the limits of memory. Black holes strip away orientation and challenge the very notion of a coherent, continuous self, inviting parallels to mystical traditions that speak of states beyond ordinary perception. At the intersection of quantum mechanics and general relativity, the study of black holes forces us to confront a crucial philosophical question: can notions of determinism and causality hold when time itself loses meaning? Inside or near these gravitational abysses, the sequence of cause and effect becomes obscured, provoking a radical reconsideration of how the universe unfolds. If time is a map we project upon experience, then black holes expose places where this map ceases to correspond with the territory. The implication is staggering. Our most fundamental categories, before and after, cause and effect, existence and non-existence, may be emergent properties, valid only within limited scales and contexts. This prompts us to contemplate whether reality is ultimately relational and fluid, shaped by observation and interaction rather than fixed in absolute terms. These reflections extend naturally into existential territory. Black holes remind us of the profound mystery underlying all existence, the vast unknown into which we ourselves are embedded. Faced with their inscrutability, one might feel a deep sense of cosmic loneliness or, conversely, a quiet humility and wonder at being part of a universe where such mysteries can arise. The contemplation of black holes, therefore, becomes an invitation to embrace uncertainty, to accept that some answers may forever evade us, and to find meaning not in definitive knowledge but in the awe and curiosity that drive our ongoing quest. In this way, black holes can be seen as cosmic metaphors for the human condition, a reminder that, despite our advances, we remain explorers not only of space but of the profound depths of existence itself. In recent years, discussions around the holographic principle have added further philosophical depth. This radical idea suggests that the information contained within a black hole might be encoded on its two-dimensional surface, the event horizon, rather than residing in a three-dimensional volume. If true, this implies that reality itself might be holographic, three-dimensional space emerging from a deeper, more fundamental layer of informational encoding. Such revelations challenge our intuition about dimensionality, locality, and the nature of reality, hinting that the universe might be a projection from a boundary that encodes all within a form unfamiliar to ordinary comprehension. Here, the study of black holes intersects with profound metaphysical questions about the relationship between appearance and essence, surface and depth. The existential shadow of black holes also forces us to reconsider human attempts to impose meaning upon a universe that may be indifferent or even unknowable. In a cosmos where information can vanish beyond horizons and where singularities disrupt causality, the narratives we construct, whether scientific, philosophical, or spiritual, encounter their own boundaries. Yet, within these boundaries lies a paradoxical freedom, the freedom to interpret, to seek connection, to find significance in mystery itself. In this light, black holes do not represent nihilistic dead ends but rather openings, thresholds into a poetic engagement with the unknown, an ongoing dialogue between reason and wonder. Ultimately, the philosophical depth of black holes transcends their astrophysical origin to touch upon the core human experiences of consciousness, reality, and meaning. They stand as silent monuments to the limits of thought and the vastness beyond, inviting us to broaden our perspectives and embrace the complex, paradoxical texture of existence. In confronting the mysteries they embody, we may glimpse the edges of understanding and the infinite horizon that calls us onward into darkness, into light, into the profound mystery that is both the universe and ourselves. Beyond the profound philosophical reflections and the remarkable advancements in astrophysics, black holes continue to haunt the scientific imagination with possibilities that seem to strain the very fabric of reality. One such unsettling prospect arises from the concept that black holes might not be the final prisons of matter and energy, but rather gateways to other regions of the universe or perhaps to entirely different universes altogether. This idea, long a staple of speculative fiction, now finds tentative footing in certain theoretical frameworks. The notion that black holes could harbor wormholes, tunnels through space-time connecting distant points, is both thrilling and disquieting. Wormholes, if they exist, could allow for shortcuts across cosmological distances, potentially enabling forms of travel or communication that defy conventional understanding. Yet their stability remains in question, and paradoxes arise when considering causality and the flow of time. Does matter entering a black hole pass through some cosmic conduit, or is it irrevocably crushed into oblivion? The lurking uncertainty here provokes a deeper unease about what lies hidden beyond observable horizons. The singularity at the core of a black hole, where density and gravity are thought to become infinite, presents a profound puzzle that defies the known laws of physics. Current theories suggest that space and time themselves break down under these extreme conditions, leaving our understanding fractured and incomplete. But some physicists propose radical alternatives to the traditional picture, suggesting that singularities might not be points of infinite collapse but rather regions where new physics reign. For instance, some models in quantum gravity envision fuzzballs or gravastars, exotic objects that mimic many properties of black holes but sidestep the paradoxes associated with singularities. These ideas imply that what we perceive externally as a black hole may conceal a far richer internal structure, a complexity beyond anything we can directly observe or yet understand. Such scenarios open unsettling questions about the nature of reality itself and challenge the neat, classical narratives of cosmic destruction. Amidst this scientific quandary is the problem of information loss, a controversy that has sparked decades of debate. According to classical understanding, anything that crosses the event horizon is lost forever, its information irretrievably destroyed. However, this notion conflicts with the principles of quantum mechanics, which demand that information cannot simply vanish. This tension has led to propositions such as the black hole firewall, a theoretical boundary that incinerates infalling matter to preserve information, but which unsettles the cherished principle that falling into a black hole should feel uneventful until the singularity is reached. Alternatively, Some researchers propose that information is somehow encoded on the event horizon's surface, in a manner analogous to some form of cosmic hologram. But if true, then the black hole's event horizon acts not merely as a point of no return but as a peculiar repository of the universe's memories, an idea both enthralling and deeply mysterious. Furthermore, the enigmatic radiation first predicted by Stephen Hawking introduces a new dimension of uncertainty. This radiation implies that black holes can slowly evaporate, losing mass until they eventually disappear entirely, releasing their contents back into the universe. But this gradual dissolution raises profound questions. What becomes of the information carried by that radiation? Does it escape intact, or is it scrambled beyond recognition? Such uncertainties hint at a universe where the memory of what has fallen into a black hole is conserved in ways not yet understood, or perhaps fundamentally altered. Beyond the puzzle of physical laws is the unsettling implication that black holes might challenge the causal structure of the universe. Near a black hole's edge, time itself can dilate to extremes, and the normal sequence of cause and effect may lose its consistency. Some speculative theories even suggest that black holes might contain closed time-like curves, loops allowing for paths backward in time. While these remain highly theoretical, they provoke unsettling imaginings of time travel, paradoxes, and the fragile coherence of reality itself. Such ideas force us to reconsider the linear progression of time and causality as absolute, suggesting instead a cosmos where the very flow of history might be wrinkled, looped, or incomplete. In contemplating these possibilities, we also encounter the chilling concept of white holes, hypothetical counterparts to black holes that spew out matter and energy, never absorbing anything. Though no direct evidence exists for white holes, some physicists speculate they could be related phenomena, perhaps the other end of a wormhole connecting two disparate regions of spacetime. If such strange objects exist, they would rewrite our understanding of cosmic cycles, suggesting not only points of irreversible collapse but also explosive points of creation. The symmetrical beauty and mystery of such pairs add yet another layer to the labyrinthine nature of black hole research. Finally, black holes challenge us to confront the limits of observation and measurement. By their very nature, black holes cloak themselves in darkness, denying us any direct glimpse beyond their event horizons. They force scientists to rely on indirect clues, the behavior of stars and gas clouds swirling nearby, gravitational waves rippling through spacetime, and minute effects on cosmic radiation. Each new detection peels back a layer of mystery while revealing deeper questions. The very act of studying black holes highlights the profound interplay between knowledge and ignorance, certainty and doubt. In this dance, black holes remain not only cosmic objects but also metaphors for the unexplored frontiers of human understanding. As we advance in technology and theory, these dark mysteries persist, drawing us ever deeper into an unknown that is not merely external but intrinsic to the universe. Black holes embody the edge where the known yields to the unknowable, where the rules that govern our everyday experience falter, and where the cosmos guards its most profound secrets. They ask us to face uncertainty with courage, curiosity, and an acceptance that some questions may forever elude final answers. In this uncharted territory, science becomes not just a pursuit of facts but a journey into wonder, humility, and awe, a reminder that even in the darkest shadows, the human spirit seeks about the light of understanding. Throughout history, humanity has been drawn to the stars, imagining the vastness of space as a canvas of mystery and possibility. Black holes, in their inscrutable nature, stand as one of the most profound invitations to explore not just the cosmos, but the very fabric of reality itself. They are not simply celestial phenomena, they are profound symbols of life's ultimate boundaries, challenging what we believe about time, space, and existence. These cosmic enigmas compel us to question the very foundations of physics that have long guided our grasp of the natural world. Consider the singularity, that infinitely dense core where known laws collapse into chaos, a point that defies classical intuition. It forces us to confront an unsettling truth: the universe harbors conditions beyond human comprehension, where conventional wisdom fragments, and new frameworks must emerge. This hints at a remarkable possibility that our current scientific paradigm is incomplete, and to truly understand black holes may require revolutionary breakthroughs in quantum mechanics, gravity, and perhaps dimensions beyond our perception. Yet black holes are more than theoretical curiosities. They have tangible consequences for the cosmic story unfolding around us. They act as cosmic engines, influencing the formation and evolution of galaxies, sculptors of the universe's grand structure. Their unseen presence shapes the destiny of stars, the trajectory of matter, and even the rhythm of cosmic time itself. In a sense, studying black holes is like decoding the universe's hidden architecture, the blueprint that governs creation and destruction on an unimaginable scale. Within this cosmic labyrinth lies an ironic tension. As black holes prize us with glimpses of secrets, they simultaneously veil themselves in riddles. The event horizon marks a boundary not only of physical reach but of knowledge. Past this point, conventional physics ceases to apply, and speculation takes the stage. It is as if the universe holds a private chamber, where the deepest mysteries are guarded closely, defying the human need for closure. This tension drives not despair but inspiration. It calls scientists, dreamers, and philosophers alike to push the limits of imagination and technology. The pursuit of understanding black holes also touches on profound philosophical questions. What does it mean for information to disappear? Could the universe be holographic, with reality encoded on cosmic surfaces? Are black holes portals to other universes, or gateways to new dimensions? These threads invite us to rethink reality itself, blending the boundaries between metaphysics and empirical science in a way rarely encountered. Moreover, black holes serve as reminders of our place in the cosmic vastness. They evoke humility, a recognition of the scale and complexity far beyond human dimensions. Yet paradoxically, they also reflect human ingenuity, the collective effort of minds spanning generations striving to pierce the veil of darkness. From Einstein's equations to the first direct image of a black hole's shadow, each milestone is a testament to curiosity's power to illuminate the obscure and transform mystery into knowledge. In this interplay of profound ignorance and relentless discovery, black holes embody both the end and the beginning. They are the final threshold of energetic collapse and simultaneously the doorway to new realms of scientific insight. Their study challenges us to embrace uncertainty, to be patient with paradox, and to find beauty in the unanswered. Ultimately, black holes are mirrors that reflect humanity's enduring quest to understand the universe, to confront the unknown, and to find meaning where meaning seems hidden. So as we gaze into the depths of a black hole, we are also gazing inward into the depths of our own curiosity, our hunger for knowledge, and our capacity for wonder. Though the mysteries remain daunting, the journey itself enriches us, revealing a universe that is as much a mystery as a marvel. In the face of these enigmatic giants, we come to appreciate that some questions may remain forever beyond reach, not as a failure of science, but as a profound invitation to continue dreaming, exploring, and imagining the infinite possibilities that lie ahead. As we venture deeper into the realm of black holes, consider for a moment that these objects are not merely cosmic vacuum cleaners swallowing everything indiscriminately, but instead harbor extraordinarily intricate landscapes shaped by fundamental forces and exotic physics. Beyond the event horizon, that elusive boundary where conventional notions of space and time lose their grip, lies a domain where our current understanding falters dramatically. Physicists have proposed that what awaits inside may defy even the foundational pillars of reality itself, space compressed so intensely that it becomes a singularity, a point where densities soar to infinity and the fabric of spacetime curves infinitely. But the story isn't so straightforward. Recent developments suggest that the singularity might be more a symbol of the limits of our mathematics than a definitive feature of nature. One of the most compelling puzzles surrounds what is known as the information paradox. In classical physics, no information about matter that falls into a black hole should ever escape. Yet, the principles of quantum mechanics governing the behavior of the smallest particles dictate that information can never be truly lost. This tension has led scientists to question whether black holes might, in some mysterious way, preserve or encode information on their surface, possibly in a holographic manner. Imagine the two-dimensional event horizon acting like a cosmic projector screen, encoding the three-dimensional information about everything that has entered the black hole. This idea, known as the holographic principle, revolutionizes our worldview, suggesting that the universe itself might be, at some fundamental level, a projection or a hologram. Exploring further, let's shift our gaze to the firewall hypothesis, a fiercely debated concept posing that an observer falling into a black hole would encounter a searing boundary of energetic particles right at the event horizon, an idea fundamentally at odds with Einstein's equivalence principle, which asserts that freefall should be undetectable. This contradiction reflects the profound conceptual difficulties black holes impose, forcing us to reconcile the subtle tenets of quantum theory with the geometric elegance of general relativity. The existence or absence of such a firewall has enormous implications for the nature of reality itself. It questions whether spacetime is smooth and continuous or punctuated by abrupt, violent transitions, a question that remains open and hotly contested. Furthermore, black holes are offering tantalizing hints about the unification of physics' two pillars, quantum mechanics and gravity. While gravity governs the vast cosmos, guiding planets, stars, and galaxies, quantum mechanics rules the microcosm of atoms and particles. Black holes, with their extreme densities and curvatures, are cosmic laboratories where these two regimes collide. One theoretical framework emerging to address these merge points is string theory, positing that the fundamental constituents of matter are not point-like particles but tiny vibrating strings. This approach also predicts additional spatial dimensions beyond the familiar three, possibly hidden within the intense gravitational fields of black holes. Such exotic mathematics aspire to resolve singularities into comprehensible structures and explain information retention. In practical terms, our study of black holes reverberates well beyond academic curiosity. For instance, the gravitational waves detected from colliding black holes offer unprecedented windows into forces operating at unimaginable scales. These ripples in spacetime, predicted by Einstein and only recently observed, help us understand the dynamics of black holes merging and shed light on the expansion history of the universe. Moreover, future experiments aiming to image event horizons with greater precision might reveal subtle clues about quantum effects near black holes, potentially revolutionizing technology derived from quantum information science. One can draw an evocative analogy in the form of a cosmic symphony. Black holes are both the deepest bass notes and the silent pauses in the music of the universe. Their presence influences the orchestration of galaxies, yet their inner workings remain the most enigmatic rests in the score, challenging physicists to decode the meaning of these silent depths. The interface where the event horizon lies is like the edge between known and unknown, tangible and conceptual, a threshold requiring new languages of science to cross. The pursuit to unravel these mysteries also carries philosophical weight. Black holes force us to ponder the ultimate fate of matter and energy, touching on questions about the birth and death of universes, the arrow of time, and the nature of reality itself. Do black holes represent cosmic endpoints, or could they be gateways to alternate dimensions or nascent universes? Some speculative theories propose that what we perceive as a singularity might instead be a bounce or a portal, a transformative hinge rather than a terminus. While these ideas inhabit the fringes of contemporary science, they ignite the imagination and drive the search for deeper understanding. As we push the boundaries of observation and theory, black holes continue to serve as humbling reminders that the cosmos is far more complex than our current models can capture. Each discovery peels back a layer, revealing new questions and paradoxes. They compel us not only to refine our physics but to reconsider the very nature of space, time, and existence. In the haunting silence of these cosmic enigmas, we find the purest expression of human curiosity, bold, unrelenting, and ever reaching toward what lies beyond the horizon of our knowledge. As we contemplate the profound mysteries that black holes embody, we are inevitably drawn into a deeper reflection on the fabric of reality itself, a fabric that, at its most fundamental level, may be far stranger and more intricate than we have ever imagined. Consider how black holes challenge the very concept of time as a fixed, flowing river. To an outside observer, time appears to slow down dramatically near the event horizon, almost grinding to a halt, while an infalling object seems to freeze at the edge, never quite crossing over. Yet, for the object itself, time passes without interruption, collapsing into the singularity with a finality that defies external perception. This unsettling disconnect forces us to question the universality of time as a singular experience shared by all observers, hinting at the relativity of our temporal existence and the possibility that time, rather than being a uniform backdrop, is a dynamic and malleable dimension intertwined with space and gravity on levels we are only beginning to understand. This mutable nature of time leads into even more profound inquiries about consciousness and our place within the cosmos. If time can ebb and flow, dilate and contract, as influenced by gravity and speed, what then is the experience of consciousness that is inseparable from the passage of moments? Are our minds bound to a steady pulse of time, or could consciousness itself be fluid, shaped by the underlying structure of the universe? The crushing gravity inside black holes invites us to confront a paradox. If the flow of time breaks down, does consciousness continue, or does it dissolve? Such questions bridge the gap between physics and philosophy, nudging us toward a future where understanding black holes might illuminate not just the cosmos, but the subjective experience of being alive within it. Moreover, black holes offer a compelling metaphor for the limits of human knowledge and the nature of meaning itself. They represent places where our empirical tools, telescopes, equations, simulations, approach their edge. Our most sophisticated theories encounter contradictions and paradoxes, like the infamous conflict between general relativity and quantum mechanics. This clash suggests that the universe harbors truths beyond the reach of any single framework or perspective. In a sense, black holes embody the ultimate epistemological boundary, a cosmic humbling that reveals how much remains unseen and unknown. From this vantage, they remind us that knowledge is not a linear accumulation but an ever-shifting landscape, where certainty gives way to mystery and mysteries inspire fresh curiosity. Reflecting further, black holes also echo profound themes from the human condition, our encounters with the unknown, our grappling with incomprehensibility. Much like explorers standing at the precipice of a vast chasm, we face a deep cosmic silence, an abyss where familiar laws seem to dissolve. This confrontation evokes existential awe, a mix of fear and wonder that resonates with the narratives of myth and spirituality throughout human history. Black holes, in their silent grandeur, become not just objects of science but symbols of the infinite and ineffable, reminding us that humility and reverence remain central to the quest for understanding. There is also an unexpected parallel between the mysterious interiors of black holes and the enigmatic depths of the human mind. Just as the singularity lies hidden beyond the event horizon, impenetrable and cloaked, so too do aspects of consciousness remain elusive to introspection and scientific inquiry. Both domains challenge reductionist approaches, both suggest that complexity and subtlety defy simple explanations. The way black holes distort space and time can, in metaphorical terms, be likened to how experiences of memory, emotion, and identity warp our internal perception of reality and chronology. Such reflections encourage a holistic worldview that embraces paradox, uncertainty, and the interplay of multiple dimensions of existence. Finally, the search to decode black holes is an invitation to rethink our place in the cosmic tapestry. They prompt us to imagine forms of matter, energy, and even existence beyond terrestrial experience. By pushing the boundaries of what is knowable, black holes encourage a radical openness to new kinds of physics, to possible alternate realities, and even to new philosophies of being. In this way, they serve as cosmic catalysts for transformation, not just of scientific understanding, but of human thought, imagination, and meaning. In facing these vast and disorienting enigmas, we are challenged to expand our intellectual horizons and embrace the beautifully paradoxical reality we inhabit, one where the very act of questioning becomes a bridge to transcendence. Black holes, with their silent pull and hidden depths, thus stand as both the ultimate mystery and the ultimate muse, urging us onward in the timeless dance between knowing and unknowing, presence and absence, form and void.